yeah, understanding climate modelling and projection. So this is, where we start talking about the tools we use to start understanding the climate and looking at the future of the climate. And we rely heavily on climate models. And there's some kind of, misconceptions about these tools by some at times, and there's also some kind of, uncertainty or doubt about, them from others. And, I think it's important to emphasize they are really useful kind of things we use. We're not ever pretending that they are a kind of perfect crystal ball kind of device that we can use, but they are pretty much our only and definitely our best tool for kind of playing out the different aspects of the climate system and how they interact, understanding them, and then seeing how they respond under different future emission scenarios. So when you look out the window, you might see a view like this, where you see, the sun, a hill, a tree, a rabbit, and some birds, and you might think, how can we understand the climate and represent it into a kind of a quantitative understanding, and then understand how it works and then how it might change? Well, of course, this is what climate modelers do, is they put equations on all of these things. Not just the kind of geophysical flows of atmosphere and eddies in the ocean that are kind of perhaps the most obvious physical aspect of the climate to represent using maths and to simulate, but all of the other aspects as well. So this is things like exchanges between vegetation and the atmosphere, chemistry in the ocean, in the ocean and atmosphere, and how that changes and how that then has effects on clouds and so on. All of this needs to be kind of quantified, described mathematically, and then simulated to kind of get a reasonable kind of representation of the world in a computer model, which is, needless to say, a hard job. And I think it's pretty amazing what climate modelers have been able to do, but none of them would say that we've reached perfection. So just representing that as a kind of cartoon, here's some of the main things that we put into computer models to model the climate. So changes in solar radiation, of course, is a huge driver of interest. So that's the various aspects of that have got to be key. But then also changes and exchanges of heat between ocean and atmosphere, then kind of dynamic processes in the atmosphere involving clouds, convection, circulation patterns, etc. But then also things like processes in the ocean, from the surface down to the deep ocean, changes and feedbacks from land features to the atmosphere, and then the drivers, the input drivers that we're providing, so changes in the atmospheric composition or what's in the atmosphere in terms of greenhouse gases and others. Then this is kind of represented around the world using a series of grid cells, so that we can simulate and the various processes in real time, including the movement of fluids in the atmosphere and the ocean. And each of those equations is solved for every time step, for every grid cell, and then that simulation is spun up. And then you can simulate different things in this model and do different experiments on it, apply different things to it and see what the response is. So here's a little quick kind of animation of some output from a nice kind of high resolution model. And you can see there's realistic looking weather systems kind of flowing around. There's kind of the usual kind of westerly circulation hitting southern Australia, including fronts, and then there's also like tropical cyclones there kind of hovering in the Pacific. So they can produce things that look really quite realistic. And if you put this alongside kind of an animation of satellite data, you'd see a lot of the same characteristics looking very realistic looking. And so it's nice to do little animations look like this, and it makes you think, oh, well, it's just like we've got the whole world in a computer. But of course, you know, we need to really critically evaluate what they're saying and what the differences are between the computer simulation and the real world. And that can inform, well, how confident are we in terms of what they're saying for our purposes. But yeah, no, the models are a pretty amazing achievement by research. They can do much more than just kind of making climate projections of the future. They're also used for doing things like understanding the past. So here's a set of climate simulations gathered together of what the global average surface temperature is if you only apply natural factors. So this is things like solar variations, etc. And we can't reproduce the temperature rise since about the 1960s. The blue lines just stay down below that. And when they respond to the volcanic eruptions that we experienced, there's also kind of longer term variability, but there's just not that strong trend in the last 50 years. Whereas if we do add in anthropogenic or human factors, then it matches it really very closely. So this is kind of part of the work of attribution. So this has been working out the cause behind certain trends or certain events, and kind of if you can only explain it by introducing a particular factor, that's good evidence that that factor, you know, is important. So just flicking back between those, you can kind of see how that works. Models are also used to do predictions or forecasts, so weather forecasts or seasonal outlooks, and also experimental area multi-year forecasts. This is actually to understand and predict what will happen in the sequence that it will happen in the future. So weather forecasts are kind of trying to give you what's going to happen on Friday, what's going to happen on Saturday, what's going to happen on Sunday. So representing that as a graph, ideally you would have a good simulation of the past in sequence, matching observations, and then going forward, that will predict exactly what will happen in sequence moving forward. This has got its own challenges, especially when you're going further out, because where is the predictability, where is the memory in the climate that we can use to make a forecast? But it's not what we're aiming for with climate projections. Climate projections are looking at what's the underlying change in the climate state and the change in the statistics. It's not saying what will happen in sequence moving forward. So I hope that that distinction is pretty clear. So to look at climate projections, looking way out into the future, we need a few things, and we need to kind of line these up. Shall I move? I'll move that over. Is that better? Yep. So we need good observations and understanding of the climate system itself to base everything on. We then need kind of plausible sets of scenarios of the future about what people do and what the resulting effect we impart on the climate is likely to be. We then need to use tools such as climate models, that's one of our main tools, to then produce climate change projections for what is the likely response to those future scenarios. So in a few ways, they're different than your weather forecasts, because they are looking at the change in the climate statistics, they're not making a prediction, and then also for hypothetical but plausible future scenarios of change. The most widely used and accepted kind of set of global scenarios of greenhouse gas emissions, the resulting concentrations, and then therefore the forcing effect or affected parts on the climate, have for the last 8 years have been the representative climate concentration pathways, or RCPs. And here's kind of the emissions in gigatons of carbon on the left, and including the concentration of carbon dioxide they get to with the little kind of starred values, moving from 2000 to 2100, and then the radiative forcing or the radiation imbalance this creates on the right, from a kind of a pathway where emissions continue accelerating and concentrations continue rising until all through the century, going right through to one where emissions are curtailed right down to net zero, the concentrations stabilise, and forcing stabilises. and there's 2 in between as well. So all of these are seen as possible, and you wouldn't want to kind of bet everything that one will come exactly true. So it then becomes a case of risk management. Like, given a range of possibilities from high to low, what's our risk space? I'm just going to make sure I've got something there. Yep. So then when we come to look at the future and look at climate projections using these different emissions pathways, we then need to consider 3 main factors, which is the internal or ongoing climate variability that we'll inevitably experience, what those different scenarios or pathways are, and the likely response to those pathways. So for global temperature, you can represent that as the kind of graph on the top right there. You always get ongoing variability. You'll also then have, what is the scenario and what's the range of possible change for each of those scenarios. And you can represent that as kind of a plume of possibilities moving forward. And the 2 plumes for each of the scenarios starting to separate as you move forward, as the effect really kind of becomes obvious. Another really useful way to kind of think about these uncertainties or these different factors that determine the future climate are using these kind of representations in the bottom. These are a little bit less intuitive perhaps, but I'll just quickly go through it because I think they are worthwhile. And that's, if you went from the year 2000 looking forward to the year 2010, 2020, 2100, etc., what's the relative importance of each of these 3 factors, and what's the total amount of variance from those 3 factors? And through time, you can see the one in the kind of middle there. Obviously, from 2000 to 2001, it'll really depend on internal variability or natural climate variability, what comes along in that year. But the further you go out, the kind of more stable the kind of future pathway looks. And what becomes much more important is, well, which emission scenario we follow. By 2100, that becomes the most important thing. But also our range of uncertainty of what the response is also important. And if you turn that into a fraction of how important each of those are out of 100%, you can kind of see these coloured blobs there. So internal variability, is the most important early on. What happens year to year. As you go further out, well, what we don't understand about the response is the most kind of important factor. But beyond about 2040, what really matters is which scenario the world follows. That's what will determine where we end up relative to the year 2000. Looking at that last representation, you can see this is more important, or the internal variability part becomes more prominent as you go to finer spatial scales. So the globe there on the left, Australia on the right, because the signal becomes kind of less clear as you go to regions, and variability becomes higher, or the other way to say it is at larger spatial scales, variability is lower and the signal is clearer sooner. So that's a really important factor to remember, is signals can become very clear at the global scale, but can become more obscured by natural variability at regional scales. So just putting this together in terms of Australian temperature and turning that into a kind of an animation here, we can see, well, if we follow a high emission scenario, we could be at the top end of that plume, we could be at the bottom end of that plume. There'll always be ongoing variability. Not every year will be hotter than the last. If we're on a medium kind of emissions scenario, the RCP 4.5, Australian average temperature could be at the top end of that plume, the bottom end. There's always going to be cooler years, relatively hotter years, etc. If we're on low emissions, then we're going to get these kind of pathways. And you can see that the outcome really varies, especially by emission scenario, by the end of the century. But the top end and the bottom end of the range is also quite different. And what we'll actually experience in any one year or any one decade will, of course, matter about the sequence of climate variability that actually comes along. So hopefully that animation kind of puts things together a little bit for you. This same representation for northern summer and southern winter, that's a kind of the kind of corresponding wet season in southern and northern. It shows how these kind of various contributions to the total, what we experience varies a lot by not only by region and how big that region is, but also by variable. So temperature in winter in southern Australia, it's not too different from northern summer, but you can see the blue contribution on the bottom there is a bit bigger. We're a little bit less certain about, what is the response to emissions. And you can especially see in rainfall that natural variability or internal variability is a really important factor of what we will experience throughout the whole century. And our uncertainty about what the response is, what the likely response to emissions is really notable, and the effect of different scenarios is less important because it's kind of overshadowed by those other two. So it's different depending which aspect of the climate you're talking about. So I hope that's a little bit of background about starting to then interpret climate change projections and some of the concepts that we use. We'll come back to some of these ideas through some specific case studies and examples, but I hope that kind of gives you the theoretical framework for thinking about climate change projections, modelling, and what explains the future change.